A stepper motor is an electrical machine that is based on the electromagnetic principle and is used for converting electrical energy into mechanical energy. It consists of a stationary stator and a rotating rotor. The stator has 8 radially positioned pole shoes, and because of the eddy current loss, it's made from thin, soft magnetic plates that are electrically insulated from each other. The pole shoes are wrapped with an enameled copper wire, resulting in a coil with an iron core, which intensifies the magnetic field lines and flux density. When current flows through the windings, a magnetic field is produced that can be visualized by field lines. The number of windings, the current, and the pole size determine the density of the magnetic field lines. The field lines exit in bundles at the pole shoe and close again through a small air gap, the rotor, and the back iron of the stator. When current flows, the windings generate a magnetic field with a strong north and south pole, which is determined by the right-hand rule. If the direction of the current in the winding changes, the polarity of the electromagnets is reversed. By switching, or turning on or off the power supply of the winding or coil pairs that are perpendicular to one another, the start can be controlled, and an alternating or rotating magnetic field can be produced. If a 4-pole permanent magnet is used as a rotor, there will be continuous attraction or repulsion between the stator and the rotor. However, with a 4-phase stator field and a 4-pole rotor, only a relatively low step resolution of 22.5 degrees will be achieved. To increase the number of poles on the rotor, thin, soft magnetic plates are applied to a permanent magnet with axial pole alignment. Through this intensification of the magnetic field, the plates themselves become a magnet with a strong north and south pole. The 2 rotor shells are then turned by half a toothpitch and trigger a polarity change in the stator. Now the rotor has 50 pole pairs with a pole pitch of 7.2 degrees. The stator design remains roughly the same, but the pole shoes have 6 teeth, each to achieve a lining of the magnetic field lines at the tooth tips. With its 8 pole shoes, the stator has 48 teeth, 2 fewer than the rotor. The combination of the relatively simple permanent magnets with axial magnetization and the additional pole shoe teeth represent the birth of the first hybrid stepper motor. Now let's look at the detailed view. If a hybrid stepper motor runs in full step mode, both phases, that is A and B, and therefore all windings, are supplied with current. All 8 pole shoes will have a strong north or south pole. There is maximum magnetic attraction between the different magnetized pole shoes and the rotor poles. By contrast, the forces of attraction and repulsion between the evenly magnetized pole shoes and the rotor poles are almost equal. The winding is energized in accordance with the phase model in 4 electrical steps, from the initial position of 0 degrees through 90 to 360 degrees. The stator field turns clockwise in 4 steps, from the initial position of 0 degrees through 45 to 180 degrees. The rotor turns mechanically in 4 steps from the initial position of 0 degrees through 1.8 to 7.2 degrees. 1 electrical cycle of 360 degrees with 4 pulses therefore corresponds to a mechanical rotor angle of 7.2 degrees. In half-step mode, the phases are switched off alternately. There is maximum magnetic attraction in each energized phase. On the horizontal axis between the South Pole stator and the North Pole rotor shells, there is maximum magnetic attraction, while there is perfect magnetic attraction on the vertical axis between the North Pole stators and the South Pole rotor shells. Energization also follows a phase model in 8 electrical steps from the initial position of 0 degrees through 45 to 360 degrees. Switching the current level from 71% to 100% and back to 71% results in a consistent current or power vector. The stator field turns clockwise in 8 steps from the initial position of 0 degrees through 22.5 to 180 degrees. The rotor turns mechanically in 8 steps from the initial position of 0 degrees through 0.9 to 7.2 degrees. In microstep mode, the two-phase currents are similar to a sine curve.